All right, colleagues and friends, let's get started. Thanks very much for being here today. It's I'm glad to see that the room is full or quite full today. So thanks for that, Rodrigo. I think you call for action, the title and the slide brought some attention. Rodrigo, he did his PhD with us in the aerospace department, supervised by Stefano and Andrea, I believe. He also was a bachelor and master student. I was one of his teachers. So he did a thesis on flow control, right? Starting to somehow combine machine learning into aerodynamics and fluid mechanics at that time. Then he moved to INTA, the National Institute for Aerospace Technology here in Spain, where he did a postdoctoral activity for a couple of years. And then in 2024, he got back to our department as assistant professor. He holds now an assistant professorship position. And he's moving now or transitioning from more fundamental aerodynamics to applied aerodynamics, still using machine learning and trying to apply that for aircraft design, looking into smaller vehicles, low dimensional and building surrogate models. He's quite active trying to establish a collaboration with INTA, which I think is quite important for the department, supervising a lot of PhD students. And well, he's going to tell us what he's doing. And first, yours, thanks for being here today, Rodrigo.
So thank you very much, Manu, for your kind introduction. I don't really know if you are here because of the title that I was setting to this presentation or because you are really interested on the topic. Anyhow, I'm going to try to do my best to keep your interest during the presentation. So the first thing is that, of course, this is a catchy title, right? This is nothing to do with politics, apart from the fact that I'm using actually the US stamping here. But the idea is that I wanted to bring you here, but there is some kind of truth in what I'm saying here or claiming here. And yesterday I was trying to motivate it somehow, and I was a bit philosophical. So I was reading about the history of aerodynamics, and I jumped into something like that. And of course I didn't do it. I am a bit lazy, as you will see. So basically I was reading for 2 hours about the history of aerodynamics, and I told ChatGPT, please, can you make for me a timeline of the main milestones in the history of aerodynamics? And he pops up with this from the ancient to medieval foundation, let's say, to the 20th century. And I don't want you to read it. I will not read it. But what I want you to see is that we have some faces or names, better said, that are quite common. And essentially, that is the Hall of Fame of physics and aerodynamics also, right? So we have Aristotle, we have Leonardo da Vinci, we have Newton, we have Sir George Kelly, and then we have our two biggest friends, which are Brandt and von Karman, that are basically the fathers of the modern aerodynamics somehow, right? So this is up to the mid-20th century. And then I said to ChatGPT, okay, what happens if we move to the late 20th century and 21st? Because I don't have that many famous names into my mind. And actually, ChatGPT kind of agrees. And basically what we have is no more names, but we have CFD as the main word, the keyword that appears here, right? So basically, we substituted these people that is studying the topic and the discipline and advancing in knowledge by a computer that is helping us to advance on it. And for me, this is fantastic. But this is telling us something, that we are relying on a machine to learn a bit, right? Even further, we focus in the 21st century topic. Even ChatGPT is forgetting about CFD, and he's already telling us that artificial intelligence is coming to help us. Not even that. He's suggesting about the next generation aircraft, and we are not still sure about what this really is, right? We are asking for proposals, and we don't really know what it is. Anyhow, this is the idea that I have in mind, and based on that, I wrote like what I consider that is happening right now. That is, we are confusing somehow knowledge with computational power, right? So the classical approach is that, yes, we have the Navier-Stokes. We can reduce the model to something simpler, and then we are mimicking the physics quite well. We understand them. We test them in a wind tunnel or whatever facility that we have, and we check and we learn from that, right? This is the classic approach. Then we jump into the high-performance approach, in which we have the CFD revolution, and basically we run simulations sometimes for the sake of running them. And actually, you see some simulations about, actually Fluent, for instance, is a company that they love, ANSYS, they love to run simulations for the sake of running just as out of advertisement. But what is the sake of that? It's just spending energy, it's just showing off. Do you really want to learn? Or are you running an expected from learning afterwards? What is the point? And apart from that, we have kind of a different approach, which is coming for the last 2-3 decades, which is trying to learn from the data. This is where I consider myself in. I don't know how to do CFD. This is why. And basically, the idea here is we already have a bunch of data. Let's try to squeeze it and take all the information that we have from them. And let's try to build this data base or data-driven models here, right? So I will be talking about surrogates a lot. When I say surrogates in here, I will be always talking about AI-based or data-driven based surrogates. I will not, because for instance, in terms of Navier-Stokes, you have LES or RANS model that can be considered a surrogate as per se of the Navier-Stokes. Okay, but in here I will talk mainly of these data-driven approaches. So based on these three ideas, I asked again ChatGPT. This is what I think that is the situation right now. Can you give me some highlights of what you think that is the situation about aerodynamics? And he popped up with this that I find fantastic, like more flops, more lift. CFD was yesterday, AI is today. Or the last one, computer power drives innovation. It's like, oh my God, we are facing something like that, right? And I was reading this yesterday and I said, okay, fantastic. I already have the motivation for my talk tomorrow. And indeed, this is what I see, right? And I think this is a disclaimer for all of us, including myself, that I use it a lot. We are using so much the word artificial intelligence, machine learning, and all that in our proposals, in our papers, and so on. And we are using ChatGPT in that way that he's actually thinking that AI is the future and will solve everything and substitute everything. He really thinks so. And I don't know to which extent the community is starting to think that. So we have to be careful with that because, spoiler alert, it is not able to substitute us, okay? So I hope you are already kind of engaged. And basically, this is the content of the talk today. I will have two main blocks. So the first one is about passing from conventional data-driven models in which we don't really care about how efficient they are. We just take, for instance, a huge neural network and we try to understand what is going on within the data. We go for something a bit low dimensional and data efficient. And the idea here is I will use two techniques for the dimensionality reduction. One is isomap, in which we try to give the geodesics. The other one is variation autoencoders. We don't really know what are we doing, but it works. Of course, this is a joke, but somehow it is. And then we have a data fusion part, which is basically, remember that I did my thesis on experimental fluid mechanics, so I want to use the data that I know to extract from experiments also in combination with CFD. And last but not least, adaptive sampling is something that we are working right now. Above all, this is something that is quite true. Well, I'm not lazy, but I'm stingy. For those that know me, this is rather true. Also in science, so I will not spend a penny on a simulation that is not worth it. So how can I tell my model, which is the simulation that I have to run next to increase information? And this is the last part of the talk today that is a work in progress. So I will not really stay much, okay? So for all the results that I'm going to show are based on this platform. So this is the XRF1 configuration provided by Airbus. This is like the soft model of an Airbus A350-ish. Okay, so it's a filtered version of this model. The database that I'm going to be using was provided by the Gartner group, the ADAG60 group, back when I was working in INTA, and it was led by Esther Andres, my colleague in INTA. And the mesh that we use is something similar to that one that you see in here. All the simulations were run in DLR with the run solver tau, okay, for those of you that are used to that. We have the whole aircraft, so the simulations were done with the whole model, but we are going to focus only on the wing. We have data either for the wing or the belly fairing. I think the belly fairing is not that interesting, so I focus on the wing, okay? And we have a flight condition that is a bit weird in the sense that we have a 2.5G configuration that is mainly because they were doing some airworthiness regulation tests and so on, and they provide us with this data. We are having run simulation, as I was telling you, and in total we have around 500 simulations. It might seem a lot, but it's not really that much if you want to generalize everything about what is going on the wing, okay? Regarding the train test split on this data set that we have, I will mainly work on something like this. So almost 500 simulations are used for training and the rest of them for testing and validating. In case I change it, I will tell you during the presentation, but that will be, let's say, the idea that I have. So as you see, we have quite populated the direction on the angle of attack, not that much in the direction of the Mach number. Okay, so that's something to take into account. And we as engineers have a bias that we think that things happening at low Mach number and low angle of attack are not really interesting because it's easy to assess. And this is rather true, but you will see at the very end in the data sample part that we are missing some information in there. Okay, and this was done by a German engineer that decided to run these points, let's say. So I will be showing results that we already published somehow, or we already contributed to the community. This one was the first thing that I did when I went to INTA. So it was more an exercise for me to learn, let's say, rather than something to publish strongly. And the idea was to make like a review of different dimensionality reduction methods combined with regressors. Okay, so here we have basically the combination of classic POD with isomap. I will explain briefly how I go into that. And we, as a regressor, use random forest in the old school side of artificial intelligence, let's say, and a neural network, a multi-layer perceptron in the new side of machine learning. Okay, that will be a bit of a naive explanation. So this flowchart is what I'm going to use. So try to keep it in mind to understand a bit the process, but just being quite fast, we have our snapshots, which are the wings. We will encode them into a low-dimensional space. And with that idea of working with less amount of data, we're going to do the regression in a more efficient way, which is this regression part in here. So we are going to jump from the parameter space to the low-dimensional space by a regression. And eventually we will use a decoder, whatever it is. In the case of the POD, it's easy, just a matter of multiplayer matrices. In the case of isomap, it's not that easy. And we will end up again with our snapshot, which in this case is the pressure distribution of that wing. That would be the whole idea. Okay? So for the case of the POD, easy peasy. I think all of you know about POD here. In this case, we are not using in a classic way. Like, let's say we don't have time involved in here. So this V that I'm calling the temporal modes is not really temporal modes. We have no involvement of time. Remember that this is run simulation. So basically what we have is different pressure distributions on the wing. These are basically 2D data because this is a surface, but we have it in a 3-dimensional mesh. So we squeeze them into a vector. This is our snapshot. We build our snapshot matrix and we perform the singular value decomposition there. So we have our left eigenvectors that are presenting us, let's say, the more energetic distribution of pressure that we can find on the wing-ish, okay? And on the right side, we have what should be our temporal coefficients, but here is no time, as I was telling you. So they are telling us how to combine, let's say, the flight conditions that we're having. So the regression operation is going to be done on the right, eigenvectors. That would be the idea, okay? This is easy, I know it, but it's still quite a lot done in the community. Okay, so there are a lot of regressors based on POD. Regarding isomap, I know that many of you know it, because I know Stefan and Andrea have been working on that from 2021, and many of you are working with them, so most of you know it. And in these seminars, many times this isomap word has come into play, but I think no one really tried to explain it, how it works and how we're going to be using it. So basically, the idea is a dimensionality reduction technique. And the idea here is that we want to keep the geodesics. Okay, we want to keep the distances between points. There are many approaches, multi-dimensional scaling, local linear embedding. I will rely on isomap. Okay, for that, I will rely on the same example as Tenenbaum, which was basically the developer of this strategy or this algorithm, let's say, which is the Swiss roll. Why? Because it's super easy. We see a 3-dimensional data, but we know it's 2-dimensional because it's a surface. So if you unroll it, you have basically a plate, right? It's easy to see. So basically what this guy is telling us is that the difference between Euclidean distance and geodesic distance matters, right? You see that the dashed line is the Euclidean distance, the solid line is the geodesic, passing through, let's say, the data samples. And we will try to keep that solid line in here, right? So the first step is to build our neighborhood graph. So we need to know which are the data samples that we have and how they are close to each other to build this network. Then we will use this network to build, which is to approximate, let's say, which is the value of this geodesic distance. And for that, there are other algorithms. We use the Floyd algorithm, which is the one that actually Tenenbaum proposes. And basically here is passing from one point to the next one, which must be a neighbor, to the next one, which must be a neighbor, and we end up to the final point that we want to reach, okay? And this is the best approximation that we can have for the geodesics. And eventually, what we do is to find this low-dimensional embedding in which we keep the geodesic, okay? That will be the idea-ish. So what we are going to do here is, instead of having a geometry, which here is easy to find because this is a Swiss roll, for us, we are not working in a 3-dimensional space. We are working in an n-dimensional space in which this n is basically the size of our CFD mesh, which is huge. Okay, so basically, each point in our high-dimensional space is a simulation. And we end up having something like that. So P is a big number, the number of grid points. we want to go to n ISO, whatever is the size of the low dimension embedding, and this is something that we have to define a priori, and we don't really know which is the size of this guy. Knowing that we have only two design parameters, the angle of attack and the Mach number, it is easy to say, okay, maybe 2 is enough. And actually, it is kind of true. But we ended up working with 3, and this has just a simple explanation. It was a bit better in terms of the whole surrogate performance, okay? Apart from that, in the following exercises, we removed this third coordinate because it had no physical insight. In fact, for those of you that didn't sleep yet, on the top right corner, you see what we really consider our embedding, our low dimensional embedding just in 2D. And in here, what we can see on this kind of broccoli-shaped low dimension space, we have that the angle of attack grows with gamma 1, which is represented by the size of the dots, and that the Mach number decreases with gamma 2, which is given by the color. So already ISOMAP is telling us that there is a relation quite well structured in our data without telling it anything about the levels. Okay, so we are not telling anything about which is the current Mach number and the angle of attack in any point. And this is good. This is already just by sight, we know what we are doing. And just by sight, we can infer if we have a hot area in which we are missing data or not. Okay, that would be the idea behind the ISOMAP. So now the problem is, imagine that we performed the regression, we didn't do it yet, either using a neural network or whatever you want, and now we have to come back. In the case of the POD, it's easy. We just multiply matrices using the left basis as something that is frozen. But in the case of ISOMAP, there is no possibility to come back in a direct way. Okay, so we rely on an approach based on K and N, so the nearest neighbor that we have around. We find them in the low dimensional space and their high dimensional counterparts, and we do a weighted average, basically. So imagine that we find this black dot, which is our prediction. We find which are the neighbors within the low dimensional space. We identify which are those in the high dimensional space, and we do this weighted average based on the distance. This is something that I didn't invent. It was done by Frank. I forgot to cite it, sorry, in 2011, okay? But it works quite well. So as average performance, I wanted to show you here, as I was telling you, this was more or less an exercise for me to understand how to couple this ISOMAP with neural networks and so on. And what we're seeing here is that ISOMAP keeps more or less the same performance and having no reduced order model or no dimensionality reduction. So like not reducing the dimensionality of the data keeps more or less the same accuracy in terms of the whole surrogate model, which is something interesting. Even more interesting if we consider a figure of merit on the complexity of the model. Here I'm using basically the RAM consumption when deploying the model. Random forest is huge, as you see. We are in the order of 10 gigabytes just for training a random forest. Makes no sense. But if we focus on the right, in which we are using a neural network for the regression operation, if we are doing a direct regression operation, we are heavy. Let's say we have coefficients on the order of 1 gigabyte, which is not crazy. But if we consider the ISOMAP, we are going to megabytes, nothing. So it's something that we can run in seconds. So that's the interesting part. So we are squeezing our data, we are just taking part of it, but we keep the information that is relevant for the regression. So that would be the idea, right? But for me, that was easy. So I basically, let me show you that result. I was jumping already to the next one. So that is a silly example. Essentially, this is for a case that is a bit tricky. Mach number was quite high, and also the angle of attack. You see that ISOMAP tries to follow quite well the trend, and it is not the case for the POD. Okay, that was kind of expected because we were having shock waves and we were having some separation also. So the POD was completely lost in that respect. So I'm going to jump into the next one, which is a bit more interesting, which is what happened if we add more variables, because angle of attack and Mach number are somehow okay, good, but it's not that much. And then we asked Airbus for another database, and they provide us with that one. So we are having angle of attack, Mach number, and then we are having modifications of the wing with respect to the nominal condition, let's say. So we are modifying the sweep angle, we are modifying the span and the thickness ratio. And based on these three geometrical variations and the flight envelope, they provide us with something like 3,000 simulations. It looks like a lot, but if you do the numbers in this 5-dimensional space within the bounds that we are given, I remember my face when I was given the database and I was looking at the Airbus guy like, are you sure that you want me to do that? and eventually We tried, and not only that, there was a meeting that I said, okay, hold my cap, because we are going to raise the bar and we are going to work in the low data limit. We realized that this is possible, and we are not going to work with the common 70% of the training data. We are going to work only with 30%. So basically the idea is with around 100 simulation, we are going to work in the whole 5-dimensional space. And of course, they were super happy. I realized that I was a bit a big mouth guy, and then I started working on that, right? So the idea here is pretty much the same. I am updating the figure here. So we start with the snapshot and the parameters. We build our encoding process through isomap, and we will have, spoiler alert, this kind of embedding. Then we will use a predictor, which in this case is a multi-layer perceptron, and eventually we use our Taylor, it's a backmapping based on a Taylor expansion to go back to the high-dimensional space. That one is a model that Stefan and Andrea proposed, okay? I will show you in a minute. So the problem here is about the dimension of the isomap embedding. So again, having 5 parameters already is telling you that you have somehow 5 dimensions in your data, right? So 5 main directions that you should find. And this is what we thought. And basically, based on that, we played a bit with the number of neighbors to construct the graph. I will not enter into detail in here. And we also work with the residual variance, that is somehow a matrix that is telling you how well you are representing your data. And we did it for 5 dimensions. This is the gammas from 1 to 5. And we were a bit lost because we didn't manage to see visually, let's say, plotting the data, any relation. So we did a correlation of our data, and we see, let me help you out in here, that basically we have only correlation between the gamma 1, gamma 2, so the first 2 dimensions of the embedding, and the Mach number and the angle of attack. The rest of that is not really represented within the embedding. And at the beginning, we were a bit lost, and we decided to use as figure of merit the average CP and the RMS CP. That would be the average CP distribution over the wing, although it makes not really much sense, but let's see how much we keep. And we see again that everything is basically given by the flight condition and gamma 1 and gamma 2. So that was a first claim that we talked to our provider of the data, that was Airbus. We were telling them, please, whenever you want to do optimization of the shape, don't mix it with the flight condition, because the flight condition will drive your aerodynamics. That was the first one. But second, we realized that the geometric modifications here were somehow embedded in the aerodynamics, in the flight condition. So basically, modifying the thickness ratio is something similar to modifying the effective angle of attack. Modifying the sweep angle is something similar to modifying the effective Mach number. And actually, isomap was relying on that, was somehow understanding this. I don't know how, but he did. And then, okay, we decided to go for 2 dimensions. And the shape of our low-dimensional embedding is something like this, okay? So we have this half donut shape in which we have isolines of gammas, which are quite well separated one from each other. So there is no jumps from one gamma to another one. This is given by the size of the dot. And the Mach numbers go from left to right, increasing, okay? So for us, it's fantastic. Something that I'm not showing you here is that the thickness of the alpha layer is given by the thickness ratio of the wing, which is interesting. So within this alpha layer, the thicker the wing, the outermost position within the alpha layer. Anyway, so what you see here is that despite the fact that we are reducing the amount of data, so this is the whole data set, this is the test set that we are going to use for testing our subarray, and just giving 30% for training, we keep this main information within the low-dimensional space. So we were happy with that. We were thinking that we can keep, which is the intrinsic features of the CP that we can more or less generalize. That was the idea here. So regarding the backmapping, I will go quite fast. I don't want to take time because you want to go for lunch, I guess. The backmapping process that I use is based on the paper by Esen Farsanik that was coordinated by Andrea Yaniro and Stefan Ischete here at the department. Is kind of the weighted KNN that I showed you before, but instead of doing a weighted average, we do it at a first order Taylor expansion between the neighbors in the low and the high dimensional space. Good. So I remember that when I was presenting this in the conference, I was a bit afraid, because if you look at the big numbers, a direct interpolation using just a neural network is better than using the isomap. And I was afraid that someone was asking me. So I prepared it, and basically I already showed the question before someone could ask me. And the answer is based on 2 cases that I chose randomly, one in which I perform better than the direct regression, one in which I perform worse than the direct regression. And these are the 2, okay? So basically you see that on top, the isomap approach is quite good. like everything is yellow, so everything is approaching to zero difference in CP, like colors are representing the deviation that we have of our prediction with respect to the original data, okay? And in the bottom one, we see the opposite, right? Like the whole wing is almost red, so we are not doing quite well. But there is something a bit more interesting if we see closely, right? If we cut some slices close to the root at the mid-wing position, mid-span position, and close to the tip, what we see is that our approach, even though in average of the whole profile, we don't do it that well, for the shock wave position and this big pressure drop that we have in there, we kind of capture quite better the feature of that shock wave. So like you see by the pointing arrow that we are able to catch how the pressure drops in here, but the direct DNN approach is kind of filtering that out. So we were kind of happy. And actually during the conference, some people were suggesting us to do some kind of clustering to perform the surrogate approach in different areas of the wing. And we are thinking of doing that as well. And we're working on that. So we were happy with that result. Then following on that, we said, okay, isomap is fantastic, but we don't really like the idea of the backmapping process. We are a bit tired of relying on an additional model for coming back to the real CP data. So we went to variation autoencoders, okay? Why? Because you are training two neural networks, one for encoding, this is our isomap, and one for decoding, this is our backmapping, but everything is trained at once. So we are training these two guys such that the reconstruction of TCP is having minimal error. And since this is variational, we are forcing not just a value of the latent space, but we are forcing a probability distribution. This, of course, we don't know, it's so Gaussian. And what we do here is, with this beta parameter, we force more or not to follow this probability distribution. That would be the whole idea. I will go quite fast in here because we have the paper out, so you can read it if you wish. So the only thing that we were a bit afraid of, because this is something that is already published, we were not the first one doing that. There are a bunch of them. But people in aircraft design didn't care much about what was going on inside the autoencoder. So the first thing was, okay, which is the dimension that we have to take and which is the value of beta? We don't know anything about this guy. So we did this analysis and we realized that there is, at least for our data set, a critical value of the beta up to which the reconstruction starts failing completely, right? Like around 10 to the power of -3, this value, if you keep rising the beta, you are lost. Your reconstruction is a bit shitty. But from that value, lower values of beta, let's say, we reach this kind of asymptote, and then the dimension becomes important. And you see that increasing the dimension means that you are providing more data to your decoder, and then your decoder performs better. Easy to understand, right? Actually, you can see that in here. I'm not trying you to understand this figure, but what we did is, even though we are analyzing from 2 to 6 dimensions of the latent space, we are going to focus on in the 2 more important latent space directions, and we are going to plot the embedding. And let's see what we find. We were looking something similar to the isomap because we already knew that there was something there that we can extract. And actually, if you look at the 2 dimensions beta around 0.008, we see something similar to our isomap embedding. It has not the broccoli shape, but we see that the angle of attack grows in one direction, the Mach number grows in another one, and already by first sight, we see some kind of dependency. And this is something that we like. So we decided to keep this 2-dimensional embedding, even though our reconstruction is worse, because we need to understand what is going on. So remember that we have a training step for the variation autoencoder in which we just care about the reconstruction. And then we have the inference stage in which we will pass from the parameters to the latent space. Okay, and in here we are not relying anymore on an additional neural network, but we will use a Gaussian process just to keep it a bit simple. So just looking at the performance of the Gaussian process, so from Mach alpha to gamma 1, gamma 2, let's say, it is independent of beta. So the values that we are exploring on beta, they didn't affect that much to the regression. So we were quite happy about that. But of course, if you include the decoding process in here and you really see which is the value of the CP, surprise, surprise, beta affects, because if we increase beta, we reduce the performance of the autoencoder. Then if we increase beta, we reduce the performance of our surrogate. Then we decided to focus on a mid value, let's say 0.08, in which we have already trained and test set quite close to each other. And we have a beta that is not 0, but is high enough to have some regularization of our latent space. I will show you just a result in which you see that still we are making quite big errors. And this is the motivation why we did 2 additional features that I encourage you to read in the paper. I will not show it here, which are the PCA preprocessing. That is a way of even reducing more our data dimension before training the variation autoencoder. And this was helping us also in the regression. And lastly, the fine-tuning. So we realized that we can quit the dependency on beta by fine-tuning the decoder again. And I encourage you to have a look on the paper if you wish, or just come and discuss. This is kind of interesting. So let's go to the second block. I think I'm going good on time. I see faces of hungry. So I'm going to focus now on data fusion and multi-fidelity. This is work that was developed by Javier Nito Centenero, one of my colleagues in INTA, and he's also doing the PhD under my supervision. And here we have an objective that is basically to mix data from simulations. It can be low fidelity run simulation with, in this case, wind tunnel data. So depending who you ask, they might say that high fidelity can be the simulation or the wind tunnel. At least in my experience, I can say that the experiments is the ground truth for me, right? The experiments is what you measure, is what you have. So this is the ground truth. And we will use this wind tunnel test as ground truth and the run simulation as a super low fidelity approximation through which we are going to try to catch everything in the wind tunnel fidelity. Okay, that would be the idea. And we are going to use 2 approaches. Bayesian gap PPOD, which is something that was published already 4 years ago. And then we proposed the multi-fidelity Gaussian process regression. Okay. So we were not confident on our methodology yet. So instead of going for the whole wing, we went just for a section. And we choose a section in which we have a bunch of pressure probes such that we can test if we are doing well or not. So note that we have the black spots in there that are only 8 pressure probes that are the ones that we are going to use as a high fidelity data. And all the remaining ones in green, which are 52 or 51, are going to be just for testing to see how well we are doing. So we are only using 8 points within our airfoil. And then regarding CFD, this section is around 200 grid points-ish. Okay, so we are focusing just on a 2D section. So the Bayesian gap PPOD, I will not focus much in here. I guess some of you know what is the gap PPOD. If not, we can discuss later, but basically it's like running a POD in vectors that are not filled completely. There are 2 ways of doing the gap PPOD. One in which the mask of, let's say, removing data from the vectors is done randomly. That could be something similar to the PIV, for instance. And another one in which you have a constant mask, which is our case, is based by the position that we have the sensors. So we have a mass sensor, which is the grid of our CFD, in which we only have 8 points of data, which are the pressure tabs that we have from the wind tunnel. And we want to fill these 51 gaps that we don't have. So we do it with a gap PPOD, but instead of solving it with a least square process, we solve it with a Gaussian process. And we end up having not only a prediction, which is the red line, but also a confidence interval that is telling us how well or not we are doing it, which is interesting. And this is something that was proposed by DLR already at 2021. And building up on that, we propose to use the multi-fidelity Gaussian process regression. And here we are going to rely on the model by Kennedy-Hagan, which is a linear model in which we are combining fidelities. Each fidelity is a Gaussian process. And the high fidelity is a Gaussian process that is a sum of the different fidelities, which are weighted by a factor that is telling you how important is each of the fidelities you are considering. So it's a hierarchical approach. You have a fidelity that is more important than another one, then you give a bit more weight to that one. That would be the idea. And actually, in this example that you have in here is the Forrester equation. You have the low fidelity value and the high fidelity value. So if you fit the low fidelity, since you have plenty of data, it's fine. You basically go on top and the confidence interval is almost 0. So fantastic. But if you use the low fidelity to try to fit the high fidelity, you end up something like that. And it must seem that it's not really nice. But if you don't use the low fidelity data and you just try to fit the high fidelity data, you end up with something like that. So maybe the average is better, but the confidence interval is huge because you don't really know what you are doing. So basically the idea here is that we want to use the low fidelity data to improve our assessment on the high fidelity. That would be the whole idea. So the pipeline that we follow is POD. We use the wind tunnel test to build the gap POD and we solve it in a Bayesian way. And this guy is going to be, for now on, our low fidelity. So we are not going to use from this point onwards the runs as a low fidelity, but the Bayesian value, which is supposed to be already at a higher fidelity. Then applying the multi-fidelity Gaussian process regression, we are able to improve a bit the average performance of the model, but mainly we reduce the intervals. Okay, that this is something that I can show you on two different flight conditions, a high angle of a high Mach number, and two different angles of attack, as you've seen here. Okay, so the idea is that we are reducing 11%, which is reasonable, but which is a bit more interesting for me is that this red area that you see in there, which is the confidence interval, is even more reduced. So we are a bit more certain on what we are doing, and that would be the idea. So, but just to finish, there we go. We are going to the last part of the talk, and this is about adaptive sampling. As I was telling you, this is fantastic, and this works perfectly well as long as you have data. This is something that we all know, and this is how ChatGPT was trained. And if you have data, you are rich because you can do with that whatever you want. This is basically the philosophy towards we are going in society, actually. Everything goes on data. If you have data for building a surrogate, you have no problem. If you don't, you are fucked. Sorry for that. So those of you that are trying to go into machine learning models, ask for your data first to your supervisor or to your boss, whatever it is. Then we realized that we don't have data. We are working with Airbus, and they are a company, they care about the money. So if you ask them for more data, they will say, okay, are you paying for that? So we said, together with Isaac and Carlos, one of our PhD students, okay, we have to develop a strategy to tell Airbus, which is the next point that we need to run. Because we cannot justify ourselves just saying we want more data. And this is the way, okay? So we are going to rely on the first model that we did, which is based on isomap. Why? Because we know it works, basically. So we have an embedding in which we have this broccoli shape again, and then we have the backmapping and the regressor, whatever it is. Here we don't care much, but trust me, it works when we have data. That will be the idea. So there are 5 main ideas that we keep in mind here. First of all is that this is a sensitive process, as I am. So basically it's important in here to realize which is the sensitivity map, let's say, in our parametric space. So which are we have to find these hot areas in which we have something important happening and we miss data to characterize it. That will be the first message. Second is that we have to choose the fittest candidate. And this is something that comes from my knowledge on genetic optimization. The idea here is identify those regions. This is fine on the first one, but you have to choose them depending on the character and discrete decision that you have for your parametric space. So if you have nothing, you can do something like lighting hypercube sampling, trying to fill the space in a uniform approach. But if you start having something, you can do, for instance, a Voronoi approach, as we did, using each sample as a corner. I will not go deep into that. Then keep them far. Don't go close to your best friend. That means if you already have points within a hotspot, try to go further. If you start overpopulating areas, you will forget about other areas. So you will start overfitting some regions and completely downsample some others. So try to keep them far. Then physics insight. This is something that is impossible when you are doing pure machine learning because there is no physics. And in fact, we don't have any equation to impose in here. So we say that the physics here is given by the surrogate. So basically the message here is if you want the adaptive sampling for building a surrogate, use the surrogate as a base of information to build your adaptive sampling. That would be the message. And finally, you have to balance your decision as everything in life. So don't only care about how well you are taking into account sensitivity, but also focus on the distance between points. So keep them far, as I was telling, and the surrogate performance. That would be the message, okay? So based on that, Isaac was training approaches on isomap and POD, and the adaptive sampling and random sampling process, okay? And as you see, the blue line is showing us our isomap surrogate with an adaptive sampling process as we were discussing before. And surprise, surprise, we are reducing the RMS error and we are increasing our R2 correlation factor. So we show that adding data is always good, as you see in the orange line. But if you add data in the correct way, it's even better, which is the message here. So we have to find a way of adding the data. Actually, this is a gift that Isaac prepared an hour ago, essentially. And, and here we are showing you the process from a very few points. So something like 40 samples on our data set. And we start adding one by one. And here we are showing the sensitivity map. So I'm not trying you to understand anything because it's a bit messy and it's going quite fast. But we have the sensitivity map, both in the isomap and in the parametric space. And we are seeing basically on top, like the residuals in a CFD simulation. So we are seeing how well we are going towards this perfect surrogate that we want to have with our database. Sorry, that would be the idea. And actually, we did it, and we plotted our isomap looking for this broccoli shape that we know that we have to have. And as we start, of course, we see no broccoli, but progressively we end up having something promising. And already after 120, 160 simulations or samples, sorry, we can see already the boundaries of this broccoli shape. We can see already something there. Note that the arrows here are representing the displacement of the points compared to the isomap embedding made with the whole database that we consider our ground truth in here. And something interesting, as I was telling you at the very beginning of the seminar, is that the problem is not having a high angle of attack or high Mach number. It's happening at low Mach and low angle of attack, which is where we don't really have such much density of point because the engineer at Airbus decided that this is easy, we don't need points there. Apparently, we do, okay? And that would be the message. So basically, we are looking for this manifold invariance here. We are still working on that. So if you are interested and you want to discuss on this, I will be super happy for that. And before you leave, again, I'm fully open for discussion and collaboration. For those that are interested, we have already a quite well-consolidated collaboration network with some national and international stakeholders. And everything that I have been showing you here has been part of the Cetáceo and the Typhon project. So I wanted to emphasize that. And just before you leave, the last message that I want you to send you is that, yes, machine learning is fantastic and we love it. And we claim money out of using this word, and I will keep doing so. But take into account that we don't really like these models in which you know nothing about what is going on inside. It's not a matter of going for huge models and let's see what is popping out of it. Try to keep a bit on insight. Try to build something a bit smaller. Try to build something in which you can go into it, you find the physical insight, and you extract information from that. So making aerodynamics great again, yes, but also smaller. That would be the message, okay? So if you have any question, I would be really happy to answer them.
See if this works. Questions? Thank you, by the way, very much for the presentation. Questions? Mario.
Okay, thank you, Rodrigo. I understand that you went very, very fast.
I was super fast.
The many different topics, so I was a bit lagging behind, I admit. I admit also that I didn't understand very well what you mean by the isomap part. So I understand the autoencoder, which is basically what you are doing also in the first part, in the intermediate part where you actually mentioned the autoencoder. Where does this nearest neighbor part, which I think is the crucial part of the isomap, where does this play in?
It's not really the crucial part, but the isomap is a way of embedding your data, but it has no way, it has no return back. So the isomap doesn't come with a close friend that is telling you how to come back to a high dimensional space. Mm-hmm. So the problem is that in POD, you have it. In POD, you have your left and right eigenvectors and your eigenvalues. If you change one of the eigenvectors, you multiply the matrices and you end up having your CP in this case. Fantastic. In an autoencoder, you have the encoder and the decoder. Fantastic. In isomap, you don't. So the isomap is our encoder. Then we do the regression and we need to come back.
What do you encode exactly with the isomap?
The CP vectors, the simulations.
So you have the full array of pressures over the wing, the different mesh points, and from there you want to go to your reduced coordinates. Indeed. But exactly that step, how does this isomap word play in? Why is this different from the encoder part of an autoencoder?
I mean, the autoencoder is just a bunch of network, operations. Yes. It's a neural network. It's a bunch of operations that are encoding the data, and they are learned together with the decoder such that the reconstruction happens correctly, right? Mm-hmm. In the isomap, you are not relying on the coding process, so you don't really care on how well.
But you still have a neural network for the encoding part. No.
The encoding part is performed by the isomap. The decoding part is performed, in our case, with a weighted average.
So what are the outputs of this encoding part? The distances between points?
No, it's the coordinates within a low-dimensional embedding that is basically something like that. So it's like
All right.
You define a priori your dimension that you are expecting to have.
And you're trying to fit the best surface that describes your data within
Actually,
the dimensionality you have selected.
A topological tool, and it's supposed to work only in those topologies that are not open a priori.
Okay. I think I begin to understand.
So it's the same as a POD, but consider as something like non-linear POD, in which you impose already the dimension that you want to go for.
Okay. All right. A very quick second question, hopefully. The beta parameter that you are talking about, what is beta? I'm not
beta is a regularization parameter.
It's a regularization in the loss that you define. All right. Okay.
So you don't only have the reconstruction here, but you also have you are forcing.
Okay, I see beta now.
Yeah. There it is. So let's say how much you care about this KLD that is telling you, which is the probability distribution of your data.
Okay. Thanks a lot. Very interesting.
Thank you, Mario. More questions? Okay.
First, thank you for the very compelling and engaging presentation, Rodrigo. I have a question on the last part, even if I understand that's a bit more under development. So if you could go to slide 52.
Or you don't remember that number.
Well,
that one?
Yes, this one. So I have a question in terms of how do you look for the point, and if that is something similar to like probability expected improvement or expected improvement.
Yeah, it could be that actually. So this is basically la gallina de los huevos de oro that we say it in Spanish, right? So basically, once you have the answer for this question, you have solved the problem. We don't really know. Actually, we started doing a Bayesian optimization process in which we are going towards the sections in which we have higher uncertainty. So we were trying to fit our error of the surrogate within our parametric space, identifying the regions where we have less information, right? But there are other approaches that you can base it on the sensitivity, and we build the sensitivity by extracting data. So imagine that you have everything. We extract a point and we see how much it is affecting. And then we extract another one and we see how much it is affecting. But there are several ways of doing that, actually. And this is not just a matter of aerodynamics or aircraft design. Like today, I was reading a paper on train design, and this is needed everywhere that you need data.
I mean, at the end of the day, it's no free lunch theorem, right? Every problem has no solution. Right. Thank you very much.
Okay. Any other question? No? Okay. Then I think we can sorry. We can just close the meeting. Thank you again. As well, maybe you can get back to the collaboration. That one. Okay, that's good, because one of the objectives of this type of talks that we're organizing for internal UC3M people is for them to show what they're doing, for us to understand also what you're doing, partners, collaborations, current activities, and also especially future activities, right, in which to foster interaction and collaboration. So I guess first yours to contact him and knock the door and start to talk about future ideas and future steps. Okay, so thank you very much, Rodrigo, and thank you for coming.